So then we're going to enter into the last part of the semester. So the last topic we're going to talk about deals with basically all of this beautiful stuff. We're moving into what is known as Lagrangian Mechanics. It's an alternative way of actually doing physics that doesn't involve vectors. And the reason for that is a lot of times it's a lot easier to solve basically what's happening in a system if we work in non-Cartesian coordinates. But as we've already seen when we talked about things as simple as spherical coordinate systems or cylindrical coordinate systems, trying to figure out and write down simply something as like the acceleration can already become a gigantic hassle. And in certain coordinate systems where it might be easier to actually work on a problem, writing down something just as simple as the acceleration may be almost impossible, at least when you're working with things like vectors. So it basically becomes essential for us to no longer work with vectors, but to work with something else. So this necessity of us having to work with something that is something else causes us to find a different way of doing basically physics instead of doing Newtonian physics, i.e. working with vectors and forces and things that we can actually feel, to find an alternative way of actually working where the only other thing we talked about so far, basically in Newtonian physics, or at least in classical mechanics, is scalar quantities. So basically we want to now change from working from forces and vectors, so things like velocities and accelerations and etc., into all scalar quantities. Now, this is something that Newton himself actually started to work on, but it took many, many people. Euler, for example, Legendre, Hamiltonian, Jacobi, Dirichlet, to name a few. So over the span of, say, 100, 150 years, a lot of different people, primarily mathematicians, actually worked into this to be able to come up with an alternative way of actually doing physics. Now, the nice thing about this, again, is now we can work in all kinds of different coordinate systems, and we'll talk about this as we get there. Usually we work in what are known as generalized coordinate systems. But we can pretty much work in any coordinate system, but now we don't have the necessity of having to work with vectors anymore. We're going to work with primarily scalar quantities. So writing down things like velocities and accelerations, typically we don't even care about the acceleration, are going to become a lot easier. So that brings us to this. So again, the ultimate goal is then to bypass working with vectors and actually work with now scalar quantities. Now, again, this is the last topic we're going to talk about in the semester, but it's broken up over 2 different chapters. Basically, the reason for that is the first part is we're going to get used to this type of notation, get used to this type of idea in a general sense, so more of a mathematical sense, apply it to certain physics topics and talk about things like that until we get more comfortable with it, and then we're going to bring it directly into classical mechanics, which brings us to what are known as the Euler-Lagrange Equations. So, now, one interesting thing that happens in physics is physical systems always want to find a way of extremizing something about that system. Now, depending on what the system is, it has a different extremum. That extremum is an extremum, which means it could be a minimum or a maximum, but it's just something which is the biggest or smallest value that it can actually be. So, for example, in thermodynamic systems, a thermodynamic system always wants to minimize the free energy. So this is a thing which is always going to be minimized. In classical mechanics, as we're going to see soon enough, this part that always wants to be extremized is what's known as the action. So pretty much in any physical system, something wants to become minimized. It wants to find something either at a minimum. So for example, everything wants to be in its slowest energy state as possible, something that's based off of in chemistry and basically quantum mechanics in general. Or it wants to be at some sort of maximum value. So basically, we're going to talk about then what's known as the calculus of variation. So what the calculus of variations does is it finds a way to extremize a function. So let's say we have something that we want to extremize. We're going to call that thing J. And this thing is going to have fixed boundary points. So let's say we're going to integrate this from some x1 to x2. And we want this thing is defined as the integral of some function f, which depends on y, which is a function of x, also depends on y prime, which is the first derivative of y with respect to x, and depends on x itself. Okay. So this is what we want to extremize, i.e. we want to find either maximum value or minimum value of this function. Now, j here is what's known as a functional integral. The reason that this thing is called a functional integral is because it is an integral which depends on a function which is a function of a function. So again, here, f is a function, but it's a function of y, but y itself is also a function of x, and it's a function of y prime, which is also a function of x. So this was known as a functional integral because it's a function of a function, or a function of functions. So basically, what we want to do is whatever thing that this thing represents. So again, here I'm not specifying what my integral actually represents. It's just some integral that I want to extremize. So basically, what I know is that this thing has fixed endpoints. So meaning if I was, say, plotting y versus x here, at some x1, this is fixed. Some x2, this is also fixed. And the value of the function, y1 and y2, are also fixed at these points. So this is my value of my function at these 2 points. Okay? Now, the idea then is we want to vary the path, y, that connects these 2 points together, and we want to find the path that then extremizes j here for whatever happens to be extremized. So for example, it could be a minimum or a maximum, but whatever the extremum of this thing is. So again, if I'm thinking about j, so if you think about kind of what j is doing, so j might do something like this. So in this case, we want to find this value here, which would then be the minimum of what j is doing. Or it might do something, I don't know, like this, which would be the maximum, so we want to find this particular value. So basically, the idea is we want to start considering different paths, which then connect these 2 points together. So let's say this is one path, this is another path. Then I might look at, I don't know, this path, possibly this path. So we're going to vary all of the different paths of y until we find the one which extremizes j either this way, again making it a local or at least a global minimum, or this way, which is then a local or global maximum, which is then the path which then, again, extremizes this function. So it might look, I don't know, maybe something like this. So this is the path y, which is equal to y as a function of x, which then extremizes the integral of j. Okay? Now, if it extremizes the integral of j, what that means then is j then is going to have the absolute biggest value it can have along this particular path, or it has the absolute minimum value at which this thing can actually have. Okay? Now, the way that we're going to do this, at least in this part, is to parameterize y in terms of some other value, let's call it alpha. So basically what we're going to do is we're going to find these different paths. So we're going to say that this path is a function of x and as a function of some other parameter, alpha. Now, here we're going to say then that's what? When alpha is equal to 0, what happens in that case is then this path becomes the original path at which I'm looking at here, i.e. the path that actually extremizes my function. So all this means then is that y x of 0 then must be equal to the original path y of x. So basically the idea is that at the end of the day we're going to take whatever alpha is, set it equal to 0, and then that's going to be the path which actually extremizes my function. Now, to do that, we're going to go ahead and say that this guy then is equal to y of x evaluated alpha is equal to 0 plus alpha, which is the variable that we want to extremize, or at least use to extremize, times some other function, which we're going to call eta of x, which is just some arbitrary function. Okay? So ultimately it doesn't matter what eta of x is, it's just some sort of function which depends only on x, does not depend on alpha. So okay, so the idea is we're going to take each one of these different paths, we're going to parameterize each one of these different paths by basically a different alpha value. So for example, here, this red one corresponds then to alpha is equal to 0, because that's the path that we actually want. The orange one here might correspond to, I don't know, alpha is equal to 1. The blue one might correspond to something like alpha is equal to 2. But again, the idea is that for different values of alpha, we have different paths which actually connect these two stationary points. So again, this point and this point must be stationary, i.e. they're fixed. They're fixed by the boundary conditions at which we're looking for. Then by basically varying alpha, we can then pull out the path that we want, and then eventually by setting alpha equal to 0, that will then give us the path which actually extremizes our function. So, this is the idea. So, in this case, what this means then is that if we take this parameterized path, our integral j is now going to become equal to the integral, again, from x1 to x2, but j now is actually a function of alpha, is then equal to the original function, f, then f now depends on y, which is a function of x and alpha, as well as the derivative, y with respect to x, which also depends on alpha, and then also depends on x. So this is now what we're going to do. So basically, again, we're going to parameterize y, which means we're going to parameterize j, and then j now is a function of alpha. Now, what we want to do is we want to extremize this particular integral, which basically means that what? We want to extremize j with respect to alpha. Now, if you remember from calculus, again, anytime you want to extremize a function in respect to something else, you have to take its first derivative, set that equal to 0, and then evaluate at the point at which extremizes that particular function. So what that means then is to extremize this integral of j, we're going to take the partial derivative of j with respect to alpha, and then evaluate this as alpha is equal to 0, and then set that guy equal to 0. Now, this has to be true for all functions eta and x. Okay? So this must be true for any arbitrary function eta which depends on x. And we're going to use that to our advantage in just a little bit. Now, for those that are more mathematically inclined, this is a necessary condition to be able to determine extremum, but it's not a sufficient condition. We'll talk more about that in a little bit. So good. So good. So basically now using this, we can now come up with what are known as the Euler Equations. So basically, what is the condition that f has to satisfy for this thing to actually be true? So let's consider our partial derivative. So we then have partial derivative of j with respect to alpha. So it's going to be the partial derivative with respect to alpha of the integral x1 to x2 of f, which then depends on y, y prime, and x. Right? Now again, y and y prime are both functions of x and alpha. I'm just not writing that for now, just for, so it doesn't take up as much room. But anyways, now here what we know is that the endpoints are fixed. These endpoints are fixed, basically meaning that we can't vary the endpoints. Those endpoints have to be the same for any particular path that which we're looking at, which basically means that we can bring alpha, or at least a partial derivative, on the inside of this integral. So it's going to become the integral from x1 to x2 of the partial of f with respect to alpha dx. But since f is a function of y and y prime, which are both functions of alpha, we can then go ahead and use the chain rule on this thing to actually rewrite this in terms of derivatives with respect to y and y prime. So it's going to be equal to the integral x1 to x2 of partial with f with respect to y, and then a partial of y with respect to alpha, plus then the partial of f with respect to y prime times the partial of y prime with respect to alpha, all integrated over dx. Now, let's remind ourselves. So what we know is that y of x of alpha, again, is equal to y x of 0 plus alpha times eta of x, which means that y prime of x of alpha, which again y prime is the derivative with respect to x, is then going to be equal to y prime x evaluated at alpha is equal to 0 plus alpha, because alpha doesn't depend on x, eta prime of x, where that's the first derivative of eta with respect to x. So from here, we can see then is that the partial derivative of y with respect to alpha is the same thing as eta. And then from here, we can see that the partial derivative of y prime with respect to alpha is eta prime. So it's going to be the same thing then as the integral from x1 to x2 of partial of f with respect to y times eta plus partial of f with respect to y prime times eta prime integrated over dx. Now, again, what I mentioned before is that eta has to be an arbitrary function. So we don't want to ever specify what eta actually is. So here, let me write it this way, eta prime is actually the same thing as d eta dx. So what we want to do is, since this one depends on eta, we want to use the fact that eta has to be an arbitrary function. We want to take this eta prime and turn that also into an eta. Now, the way we're going to do that is to use integration by parts, right? Because as we talked about before, the reason of using integration by parts is to transfer the derivative from the one term to the second term. Okay. So let's do that. So let's look at that second term and let's use integration by parts. So good. So I have the integral x1 to x2 of partial of f partial y prime d eta dx dx. Let's use integration by parts by this. So here, integration by parts, we're going to use that u then is equal to the partial of f with respect to y prime, and then dv then is equal to d eta dx times dx, which is the same thing as simply d eta. Which means that v then is simply equal to eta. So this is then equal to u times v, so it's going to be the partial of f with respect to y prime, times simply eta, evaluated from x1 to x2, minus then the integral x1 to x2 of, so now we're going to get what? du, so du then is going to be d dx of partial of f with respect to y prime, times then v. So this is going to be the same thing then as eta times d dx of partial of f with respect to y prime dx. Okay. Now, one thing that has to be true about eta, again, is that the different paths at which I choose, so again, all of these different y of x of alphas, all have to be equal to the same value at the boundary, which basically means that when you have y of x1 of alpha must be equal to y of x1 0. Right? This has to be true. And this also tells me that y of x2 of alpha must be equal to y of x2 of 0, right? When alpha is equal to 0. And again, the reason for that is, again, if you think about the path, these 2 points are fixed. So as this thing is moving from here to here, what that means then is that what? The value of eta at the 2 different boundaries must be equal to 0. Right? Because the only way to get this guy equal to 0 based off the original function is that eta evaluated at the boundaries must simply be equal to 0. So since eta is equal to 0 at the boundaries, that means when I evaluate this, I evaluate eta at the boundaries, which means this whole entire first term has to be equal to 0. Okay. Which means that using integration by parts, this thing is just going to become the integral x1 to x2 of then d dx of the partial of f with respect to y prime times eta dx. Oops, with a negative sign. So now I'm simply going to take that term and put that in here. So again, all that's going to happen is this is going to become a negative sign. I'm going to move the derivative from here to here. So now this is going to depend on eta, and this is also going to depend on eta. So let's write all that. So finally, what I get is So I get the partial of, move this over, partial of j with respect to alpha then must be equal to the integral x1 to x2 of the partial of f with respect to y minus d dx of the partial of f with respect to y prime, all times the function eta, which depends on x, dx. Now, again, from here we're going to say that this guy, evaluated at alpha is equal to 0, must be equal to 0. Now, from here, explicitly, nothing here depends on alpha. I mean, there is an alpha embedded in here, there's an alpha embedded in here, but the way in which it's written, this thing doesn't explicitly depend on alpha. So if I set alpha equal to 0, I'm not setting anything here equal to 0. But, since this thing has to be equal to 0, so it's going to be equal to the integral x1 to x2, partial of f partial of y minus d dx partial f partial y prime times eta dx. Okay? So again, simply setting that alpha is equal to 0 doesn't set anything here equal to 0 because there's no explicit dependent on eta, or sorry, on alpha, even though there is an alpha dependent here. But again, that's just going to bring you to the path y, which actually extremizes my function. Now, since this thing is equal to 0, there are basically two options to set this thing equal to 0. Either eta itself has to be equal to 0, or this portion of the integrand has to be equal to 0. Now, let's talk about eta equal to 0. Well, if eta is equal to 0, that's a specific function that we're choosing, that eta is equal to 0, which is kind of counter to what we said, which was eta was some arbitrary function. So if eta is some arbitrary function, we can't automatically now say, well, eta is equal to 0 because we went from an arbitrary function now to a specific function, which basically breaks everything that we just talked about. So what has to be true then is to make this thing equal to 0, this integrand then must be equal to 0. So using this condition, we then have that the partial of f, which is the original function of the integrand, or the functional, partial derivative of that with respect to y, minus then d dx of then the partial of f with respect to y prime, must all then be equal to 0. So this thing here, this is what's known as Euler's equation. So Euler's equation then is the sufficient equation that we need to extremize the integral of j by putting bounds on then f. So once we know what f is, then we can solve then this differential equation to then determine exactly what f is. Once we know, or sorry, if we know f, then we can solve this guy, and then once we do that, then that's going to determine the path at which actually extremizes this integral of j. So, this is what, again, is called the calculus of variations. So the calculus of variations, again, is that we have two fixed endpoints. We know this thing has to be fixed at the one point, has to be fixed at the other points. We're simply going to vary the path until we find the one which actually extremizes our integral j. Again, j can be a local maximum, can be a global maximum, or it can be a local minimum or global minimum. Doesn't really matter. It doesn't necessarily state which way it has to be. It doesn't have to be a maximum or a minimum, at least at this stage. All that matters is it is some extremum. It's some maximum value or minimum value. So the path which actually extremizes our system here, again, whatever the system is, whatever j happens to represent, but again, what actually extremizes this is the path which is determined by this Euler equation. So again, once we know what the integral is, we can read off of there what the integrand is. Once we know the integrand, that is f, and then we simply take partial derivatives of that with a full derivative, and then from there we can determine the path that actually extremizes our system. So next thing we're going to do is we're going to start looking at some examples of this. And again, all of this is going to carry over into the Euler-Lagrange Equations, what's known as Lagrangian Mechanics, which will allow us to determine everything we ever wanted to know about our system, but now using scalar quantities as opposed to vectorial quantities, as we'll see as we get there.